The Electric Auto Shop course includes a calculation spreadsheet, which you would open up just like any other Excel file. You can copy it from the disk to your desktop or leave it on the disk and open it. It's probably better if you put it in a place where you can use it and save the changes you make to it. Start a new file, keep the original on the disk, start a new file on your desktop. So here we're going to open the spreadsheet and take a look at a few of the functions. You'll see 9 tabs at the bottom of the spreadsheet. These are the worksheets in the file that we'll be working with. They are acceleration, climbing, formulas, weight, drivetrain, cost of EV versus internal combustion, RPM calculations, wire calculations, and drag. So let's start with the acceleration sheet. We'll open it up and take a look at it. The purpose of the acceleration spreadsheet is to understand how the vehicle uses energy while it's accelerating. For example, we can see that in order to accelerate from 0 to 60 miles an hour in 10 seconds, it requires half the energy that it would take to accelerate from 0 to 60 miles per hour in 5 seconds. 501 foot-pounds compared to 250 foot-pounds. This makes logical sense. If you think about it, it's better to save energy by accelerating more slowly. Even with our gasoline vehicles, we get better mileage. So you can look at the figures on this worksheet and see how the differences are applied when we accelerate at different rates. Okay, so let's take a look at the next sheet called climbing and see how some of those relationships and ratios are correlated. So our climbing worksheet shows the energy required for climbing and for maintaining a constant speed. So you can see in the spreadsheet how climbing an incline correlates to increasing speed. For example, it takes the same amount of energy to climb a 5-degree incline as it does to increase speed by 1 mile per hour. And that climbing at 25% grade requires the same amount of energy for every 5 miles per hour increase in speed. So we'll move on to our next worksheet, the formulas references. And you'll see that this is a listing of 13 different formulas used to calculate various values, mostly energy use values related to driving a vehicle. So these reference points should be good reminders for you when working on other parts of the spreadsheet to calculate different parts of the vehicle: power, wheel RPM, torque, mass, and speed. So use this part of the spreadsheet as a reference point. Next, we'll look at the weight spreadsheet. We use this spreadsheet when we do a conversion of an internal combustion car to electric. We take out a bunch of internal combustion components and replace them with electric drive components. And we want to replace the weight distribution the same way as it came as an OEM vehicle. So we're going to weigh the car before we take it apart, before we take out the internal combustion components, so we know the distribution of the weight. And then when the internal combustion components are removed, we'll reweigh the car and determine how to replace that weight with electric vehicle components. So we're pointing out here that the vehicle had a 60-40 weight ratio from front to back, and we want to do the same with our electric vehicle components. We maintain the front to back ratio, but also the side to side ratio. So our next spreadsheet is the drivetrain. And this worksheet shows us the comparison of front-wheel drive versus rear-wheel drive on drivetrain efficiency. And you can see, looking at these numbers, that they're very consistent. You'll find that drivetrain components and trying to optimize them are usually a little bit of an overkill for electric vehicles. But we'll see that the front-wheel drive vehicles are slightly more efficient than rear-wheel drive. So here we can see front-wheel drive at 91% efficiency and rear-wheel drive at 90% efficiency. Okay, next we'll look at the cost between driving an electric vehicle and an internal combustion vehicle. You should note when using the spreadsheet there are a couple things missing, such as the cost of the electricity to recharge the battery, your insurance, and other costs, other smaller costs. So we see the tune-ups and maintenance, but if there are other costs that you can remember or think of that you want to add in, just type them in and put them into the calculation. You can feel free to work with that on the spreadsheet and add in your own parameters. You may consider that different types of electricity may cost different prices in your area. And electricity in different parts of the country may cost different rates. But we can do some changes here. If we change the price of cost of gasoline to $10 a gallon, we can see our operational costs will also go up based on that increase in the price of gas. We're using 4. It's a pretty common price nowadays, but that can change obviously at any day, go up or down, probably up. So you can see what that does to your annual budget for cost of fuel. So you can play with these numbers and see the different results you get. Okay, so next is our RPM calculation with different types of gearing. So on this spreadsheet, you can change the red values to match your vehicle. So you need to know a few things in order to do this. You need to know the gear ratios of the transmission, as well as the final differential gear ratio. You need to know your tire size, and these factors, once you enter them, you can compute the approximate revolutions per minute required for each specific speed. So let's just talk about what's going on this spreadsheet. We have a particular vehicle entered in here. The tire size here we see at R185 by 75, and then we've got 14-inch wheels and a standard Volkswagen transaxle. So in order to drive 60 miles per hour in first gear, the motor must spin at 12,668 RPMs. That's not really very practical, so we don't want to drive 60 in first gear. That also makes pretty logical sense. In second gear, we would require 6,800 RPMs and 4,200 RPMs in third gear. And then on down, you can see fourth gear, 2,900 RPMs. So if you have direct drive, you can look at the 2 columns under fixed gear ratios to determine motor RPM. And then if you know the maximum motor RPM, you can see the maximum speed allowed by that revolutions per minute. If you were to change the tire size, changing the circumference of the tire, this changes the number of revolutions required per mile and affects the calculations. So if we're building a car by scratch, we can use these calculations to put in the components that match the way we want to drive the vehicle. So next we'll look at our wire calculation sheet. This is another document where you change the red values to match the vehicle you're using and determine which size wire to use. Also, just to remember when working with this sheet, don't change the wire size OK or wire size too small functions at all. That's the result of your calculations, and you don't want to change the formula. So you can enter different parameters here and see the different results as you put them together. So our next worksheet is the aerodynamic drag calculation, and we'll take a look at that one. This shows us the amount of drag on each part of the vehicle. It's interesting to note here that the rear of the vehicle contributes the most significant amount to the drag of the vehicle. And you may want to talk about why this is the case, why this is true. If you've seen electric vehicles driving around, you may have noticed their shape. Notice how the rear part of the vehicle is rounded off and is made narrower usually than the front part of the vehicle. If you think about how this works in nature, as a drop of water falls, it rounds off like a teardrop or a raindrop. Starts off round and then it rounds off, or tapers off, excuse me, at the top as it drops through the air. So electric vehicles are designed this way. It's the way naturally that matter moves through air. It's more natural for it to be the air forming around it and needing a narrower escape at the back part of the vehicle. So looking at our numbers again, we'll see how the math proves this out, that the rear of the vehicle is the very most important part of the coefficient as we understand drag and aerodynamics. So if you're using the original file, it's probably good not to save changes, but if you have a copy on your desktop, you can save the parameters you've entered for the calculations spreadsheet.